Hello everyone, and welcome to this session on multi-population mortality modeling. My name is Nadine Ouellette. I'm assistant professor of demography at the University of Montreal in Canada, and I will be moderating the session. We have two presenters. Each will be allowed 20 minutes to talk, and then we have the privilege of having Leonid Gavrilov for discussion. He will take approximately 15 minutes, which will leave us hopefully 15 minutes for questions. So please, the questions will be at the very end of the session. Write them down for each of the presenters if you have any comments regarding the discussion as well. So without further ado, we should start with Johannes Schupp, which is a consultant at the Institute for Actuarial Financial Sciences, a consulting firm that is based in Ulm, Germany. The focus of his work is on the development and implementation of innovative life insurance product and actuarial biometric models. He is a PhD student in actuarial science at Ulm University. His research topics focus on mortality modeling and the identification of long-term changing mortality trends. He's a member of the German Society of Actuaries. I will leave the floor to you, Johannes, and we will move towards the first row to make sure we can see the presentation. Please feel free to sit there if you want, or you can stay there.
So thank you very much, Nadine, for the kind introduction. First, the work I like to present you today is called Calibrating Mortality Processes with Trend Changes to Multi-Population Data, and it's a joint work with my colleagues Matthias Berger and Justin Schönfeld. I would like to first give you an introduction why it's a good idea to model mortality with a model with trend changes, which I will then specify, and then we will look at in more detail at parameter uncertainty in the case of one singular population. Here we will look at the population of U.S. males as an example, which we will also see in a numerical example, and then we will extend that approach to a multi-population view, first from a theoretical perspective and then also with a numerical application here. Throughout the examples, we will use data of the Human Mortality Database. So let's start with a figure here. You can see the log of the death probabilities of 65-year-olds in several countries. We see a general decrease of the mortality. However, the decrease of mortality is not constant. We observe several changes in the speed of the improvement. For instance, when we look at the 1970s, over here, we see several trend changes in most countries. Also, when we look at the recent evolution, there might be some irregularities, maybe another trend change in some countries. And also, when we look further into the past, there are some signs for trend changes also in very early times. So we have in many populations, we observe trend changes in the historic evolution. And that has been identified by many other authors as well. However, in most of these applications, we only observe a very small number of such trend changes. So in most examples, we observe 2 or maximal 6 trend changes. And when we look at this from a statistical perspective, then it's always some kind of larger uncertainty when we estimate parameters from only a small number of observations. So here it can make sense from a statistical perspective to combine data from different countries to improve the estimates. There's also another perspective. Let's consider we are the risk manager of a pension fund, or if we're exposed in a country with a very small exposure, then there is typically a very large volatility in the data, and also in some cases the data history is rather short. Then we might have difficulties to estimate a reliable mortality trend in that cases. So also here as the underlying drivers of the mortality should be somehow linked or related in neighboring populations, for example, here it also makes sense to use data from related countries to improve the forecast for a specific or a singular population. So we model mortality with trend changes, and first in that part of my presentation I will introduce the trend change process we will use. We use the model of Cairns-Blake-Dowd as an underlying mortality model, which might be familiar to some of you. So here we have a linear formula for the logit of the death probabilities, time and age dependent. We have two time-dependent parameters, which is kappa 1 and kappa 2, where kappa 1 represents the overall development in mortality. So here we will see a decrease in the values of kappa 1, which comes along with the improvements in mortality we observed throughout the last years. Then kappa 2, the second time-dependent parameter, represents the slope of the mortality curve, and here we see with a larger value of kappa 2 we will see a steeper mortality curve, and vice versa. We multiply the kappa 2 parameter with x minus x bar so that we get the slope of the mortality curve here. Now let's look at the kappa 1 process for US males here together with our calibrated mortality trend. As I said before, we see a general decline in the parameters which comes along with the improvements in mortality, and for that specific trend we observe 4 trend changes here. So the last trend change was somewhere around 2000 maybe, and that's why we have a large uncertainty, a parameter estimation uncertainty here. Maybe there has been another trend change in one of the latest years, but we haven't identified that trend change possibly in that realization. But however, in a situation where we have 5 or 6 trend changes, and that we will see in one of the next slides, this trend change also is included here. Or it's the other way could be possible. There could also be only 2, maybe over here and over here, 2 major trend changes. So there's a large uncertainty with that trend change estimation. Now let's look at a little math here, at the mathematical formulation of this trend process. At the next slides, we model the period effects of the CBD model with continuous piecewise linear trends. And once in a while, we observe random trend changes in the slope. And around this trend, we observe an annual fluctuation or a noise term. So we start with the noise term here. We model the period effect with the trend process. So this was our green line we've seen at the slide before. And then we have a annual fluctuation around that trend. And here we use a normally distributed random noise here with mean 0 and a covariance sigma. Now when we want to extrapolate our trend process, the green line, then we extrapolate it with the value in the year before plus the current slope of the trend. And as we've seen in the figure, once in a while there's a trend change in that trend, and this is the case with probability p. So with probability p, we observe a trend change. That means a change in the trend slope. And in the other cases, so in with a probability of 1 minus p, we don't observe a trend change and we simply remain at the current trend. In the case of such a trend change, then we need to model the amount of that trend change. This could either be positive or negative, with a large or also a smaller amount. And then here we use a decomposition into 2 random variables, st times mt, where st stands for the sign of the trend change, so plus or minus 1, and mt stands for the absolute magnitude of the trend change. And here we will use a log normal distribution with parameters mu and sigma over here. And for the sign of the trend change, we simply assume a Bernoulli distribution which takes values minus 1 and 1, each with probability 1/2. So when we look when we want to make forecasts with such a trend model, then we need the following parameters to be estimated. We need to estimate the trend change parameters, which is the trend change probability P, and the parameters of the log normal distribution, mu and sigma. Then the values where we start our simulation, so the current value of the mortality trend and the current slope of the mortality trend. And we also need to estimate the volatility structure of the annual noise. Now let's look at the involved parameter uncertainty here. As I said, we typically have to estimate three kinds of parameters: the trend change parameters, the starting values, and the covariance matrix. When we look at the trend change parameters, we observe a large amount of parameter uncertainty. And also when we look at forecasts, the influence is quite huge. So if we misestimate the trend change parameters, then our forecasts are influenced massively. The same is true for the starting values. However, in that case, we observe a rather case-specific uncertainty. For some populations, the uncertainty in these two parameters is quite large. In other populations, there's hardly any uncertainty here. So this is very case-specific and very population-specific. However, also, these two parameters have a potentially large influence on forecasts, as the shape of forecasts will change according to the latest mortality trend. And the third parameter, the covariance matrix of the error terms, this has typically a very small uncertainty, as we have observed up to 100 or even more historical errors. So we have a large sample to estimate the volatility matrix from. And also when we look at forecasts, the influence of these parameters rather negligible, as it's only a 1 year, it has only a 1 year influence and disappears afterwards. So when we look at uncertainty, we should focus on the first two parameters, where the trend change parameter can be compared across populations, and the starting values is rather case specific. So we will focus on the trend change parameters here. And here we have basically two main sources of uncertainty. First, the actual number of trend changes is unknown, as our data is noisy, as we have noise in the data. So our estimation approach may estimate a weight which is the largest for, say, 4 trend changes, but also other numbers of trend changes can have a weight which is significantly different from 0. These weights are part of the historical calibration, which was addressed in earlier works of Matthias Berger and mine. Second, if we assume that the actual mortality trend is known, there's still some uncertainty about the actual value of these trend changes. And here we can use the maximum likelihood estimation that provides also estimates for the approximate standard errors of these trend changes. So let's look again at the numerical example. Here again, U.S. males, kappa 1 of the CBD model. We have different numbers of trend changes from 2 to 6, which always have a weight which is significantly different from 0. And the same holds true for kappa 2. Here we observe 2 to 5 trend changes, and we can assign for each of these trends a specific probability weight. So now let's look at the same trends for different countries. As I said, we use the human mortality database. We use 16 populations here, males and females, and we use the age range 60 to 109, and we'll focus on the trend change parameters. As I explained, the others are rather case-specific, or as the covariance matrix, not that important. So here are the estimates for the trend change probability P, and we see females in red or orange and males in blue. We have central estimates for each of these populations. So we have the population here on the y-axis, and then always an estimate for females and males. And we see that all the 32 populations, when we combine women and men, have somehow similar estimates. And in most cases, the central estimates, represented here by the dots, are in the confidence intervals of the other countries. And basically the same observation can be made for the parameters of the log normal distribution, mu and sigma. So we can observe a somehow similar behavior in the trend change parameters across these 32 populations, and hence it can make sense to combine these populations when we want to make estimate for our specific population. Now let's look at the parameter uncertainty in the multi-population setting. As I said, we observe similarities between the trend change parameters across different populations, and we will now analyze different approaches, 5 different approaches, to use these assumptions on the similarities about the parameters in the different populations. And we start with the assumption that the parameters are actually equal in all of these populations, and then we move forward and say, okay, they are only somehow similar, and in the last step we say that they are similar, but we don't have any distributional assumption here. So let's look again at the mathematical formulation here. We focus on the trend change parameters. We will denote it with theta here, which is the trend change probability, and the parameters of the log normal distribution. We have 32 populations, capital P, where the index small p denotes a specific population, and we have the variable np, which denotes simply the number of the data points for a specific population. So with larger populations, the value of np gets larger, and also in the other way around. Then let's denote p star as the population we are specifically interested in. This will be, again, US males. And finally, we use a weight VP, which denotes a weight for each population. Here we use a larger weight for populations where we have a larger data history, and we use a smaller weight for populations where we only have a few observations. Here also other specifications can make sense. So now let's look at the 5 approaches. I skipped most of the mathematical details here. Of course, they can be found in the paper. The first approach assumes that the parameters of the trend change assumes that the trend change parameters are actually equal across all populations, and hence we can use a maximum likelihood estimation of these parameters based on all observed trend changes in the 32 populations. The second approach, the weighted average, here we don't use the equality assumption anymore. We use the assumption that the parameters are actually same, but from an unknown distribution, and we use an estimate for the common trend change parameters simply as the weighted average of the population-specific estimates. The third approach here on the upper right-hand side, which is rather similar in some senses. Here we use a parameter sampling, so in a simulation we simply draw from that population-specific parameters, where each population has a weight of VP, which we specified on the slide before. The fourth approach over here is a credibility approach. This can be useful when we're quite confident about our population-specific estimate. Then we want to increase the influence of that specific population. For instance, in the numerical example we see on the next slides, we increased the weight for US males to a half. Again, also other specifications can make sense here. And the fifth approach, which is the Bayesian approach, here we use prior based on the weight. So we say that the population-specific parameters have a prior probability which is equal or proportional to the data length, and then the realized trend process provides some additional information such that we adjust that weight to get the posterior distribution here. Now let's look at the results. We here see the trend change probability for kappa 1 and kappa 2. We see on the first is the individual calibration, which we already seen before, and then we see the estimations together with the corresponding uncertainty with the 5 different aggregation techniques. We see that the central estimates, which are the dots, they in most or in all cases they get smaller, which is a result as we estimate a rather large number of trend changes for U.S. males. So the individual calibration has a rather high central estimate compared to other populations. What's also very interesting here, we observe that the maximum likelihood has the smallest evolved uncertainty. This is also true when we look at the trend change parameters mu and sigma. The average and the sampling show somehow similar confidence intervals. That's what we expected, as those approaches are somehow similar. When we look at the first parameter of the log normal distribution at the mu, then again we observe the smallest confidence interval with the maximum likelihood estimation. However, average and sampling and also the credibility approach, here we observe a larger uncertainty for the parameter. However, we think that this is mainly systematic uncertainty, as we assume that the parameters follow a specific distribution and not unsystematic uncertainty as it was for the trend estimation originally. Now let's look at the forecasts. When we look at the forecasted remaining period life expectancy for 65-year-old U.S. males, we observe the dark green confidence interval with the individual population, and we see that all aggregation techniques resulted in smaller confidence intervals. We see that the credibility and the Bayesian approach are somewhere in the middle, and that the confidence intervals are the smallest for the maximum likelihood approach. So let's come to the conclusion. We see in that example of US males that the uncertainty is reduced when we aggregate data from different populations. However, also the opposite can be true. If our population-specific parameters were rather large, then the opposite would be observed. So we see that an aggregation of data about trend changes from different populations can be helpful to better understand the trend change parameters in that model. Thank you.
Thank you, Johannes. So our next presenter is Xiaoming Liu. She's an associate professor in the Department of Statistical and Actuarial Sciences at the University of Western Ontario in Canada. Her research interests lie in the area of actuarial science, mathematical finance, and stochastic processes. In particular, she focuses on mortality risk modeling and its related problems, such as pricing and risk management of insurance policies with the consideration of different risk factors. So please, Xiaoming, Control L.
Yes, I can do it. Thank you. All right. So my topic is actually not about multiple population. I just realized I'm in this session, but I'm not doing multi-population in this talk. Just want to clarify. I guess they don't know where to put me, so I'm in this session. All right. So I will start from selfie project called Every Day by photography Carl Baden. He is in Boston College. And he started this selfie project from February 22nd. It's not any particular day in his life, but there are some special events happen on that day, the day before, February 22nd, 1987. So he started this project. He was age 34 at that year. So what he did is he take a photo as similar as possible each day, okay? And except the first day he wear a shirt, and all other days he was naked, and he take a photo of his facial appearance in as similar as possible approach. So the reason I am interested, this is him. He has been doing this project for 32 years now. And this is a photo of him in real life. I think he's handsome than the photos he took in his selfie project. And this is, he was at his own exhibit, a photo taken almost 30 years anniversary of his project. So the reason I wanted to start from his project, because we have a common interest. We are interested in aging process. And you can see many of the methodology I use is highlighted here in how he talked about his project. He said the idea is to make everything that he can control as similar as possible, so that the only variable in that project that he can't control is the aging process. I think I'm using a similar approach like his. So there is some comments. One is the comments from Boston Gallery owner, Howard Yatsky. I don't know how to pronounce his name. He said it's from his photos. Actually, I want to go back to the photos. He has more than 11,000 photos in that 30 years. Taken every day. And the photos shown here is every 3 years, like 87, 90, 93, in every 3 years apart on the same day, except this is the day he took after his cancer treatment. Okay, so he has a cancer between 1999 and 2002. Okay, so this is a longitudinal data connection. So the comments by observing those photos from Howard is both personal and universal at the same time, because everyone can relate to it, and we are all going to die, and we are all witness the aging process through our own life. Okay, so that's something from a gallery owner. Here is my comments. I am not. My comments is much more boring. I am just looking at the factual aspect. Carl Baden provides an incomplete sample of his daily facial photos for aging effect demonstration. That's how I visualize his project from my personal research interest. My another comment is his underlying aging process is observed as long as he is alive. Imagine he died, then we wouldn't be able to continue observe his aging process. So that's some of the comments related with that selfie project. I have a larger comments I called a dilemma about aging. So you see, there are many projects talking about aging. Aging is something so real, so tangible, right? Through that project and through many other projects and many of the research results, actually from this symposium, aging has demonstrated itself to us in so many ways through every life who has ever existed on this planet over the past thousands of years, maybe even millions of years. But the quantitative study of aging is still in its infancy. Some may want to argue about this statement, so I want to justify why I think quantitative study of aging is still in its infancy by examining these three questions on how we define aging, how much and how little we know about aging, and how aging is modeled at present. So aging is defined. I found this from John's definition, his paper in 1956. Aging is a genetic determined, progressive, essentially irreversible diminution process with the passage of the time. And it can be further specified as the deteriorating ability of the organs or parts of the organs to its environment, and it's culminated in the death of the organs. So, I summarize there are two important features in the above definition. One is that aging characteristics are really described in this relative term. It's not absolute. It's not as accurate as we would like as a researcher. So I say it's relative. It mainly tells us this progressive, irreversible process that we are worse as we age. But in what way? It's not that clear. It's a little bit vague from my perspective. Another important feature is aging is actually defined or better understood through aging effect, not aging itself, right? Like the effect of aging is the increase in death rate, but that's not aging itself. So that's my argument here. But you may challenge me by saying, hey, you refer to a definition in 1958, too old. So this is the latest results I just got from British Actuarial Journal. It's organized by Institute and the Faculty of Actuarials in UK. In their latest edition, they summon a group of the people in this area talk about genomic underpinnings of human lifespan. I'm not going to go through details, but a brief picture is in middle 90s, the single gene disorder genetic testing are able to identify mutations in a single genes, and that can be the cause for a disease, a cause effect identification. But moving on to multifactorial disorder that has meaningful epidemiological, I can't say that word. Clinic meaningful way of interpret it, it's become much more complex. And the reason for that complexity is because we are right now talking about small effects and from many genomic mutations, and we are uncertain about which cause what? So I use the uncertainty principle as a metaphor to explain the situation. So moving on. So how is aging is modeled in the past? Everyone in actuarial area are familiar with the famous Gompertzian model. Using the mortality model he presented, that's aging effect. And many times we forgot he proposed that to explain aging process. Okay? And myself, when I am interested in modeling aging process, I do relate it with mortality because really we have to be alive so that we can observe the underlying aging. Okay? So what I am asking myself is, okay, this is the situation, what we can do better to reflect our understanding. Okay, so I have to recap a little bit the results in 2007 publication in North American Actuarial Journal, and we proposed this Markov aging model, and it's by finite states, and aging is moving progressively forward, irreversible. It's an internal process of the deterioration of the physiological capacity. And the death rate we observe is increasing. It's just because of that aging effect, but we can use it to identify aging. Okay, so the deterioration makes life more susceptible to death, failures of biological systems, and that's consistent with our observation. So the first contribution in that work is we differentiate the aging effect, those errors, death from specific physiological capacity is the aging effect. And we model aging explicitly. We distinguish these two. And then, of course, people has been asking me, you don't observe aging-related mortality. Yes, that's true. So I have to embed my aging model into a larger picture to the observed mortality. Observed mortality contains other death causes, not just aging. So there are some accidental death causes at youth age. There are some background deaths for whatever reasons. So I embedded my aging model into a larger picture so that it can explain the aging-related mortality and also can be additive elements to explain the whole observed mortality rates. So that's what we did in that model. We do all statistics. We match the model mortality rate with the observed mortality rate, and I analyzed 3 cohorts, and they are very different, but one simple model is able to capture 3 very different patterns. Okay, so I propose that model. I use observed mortality rate so that people can believe what we propose is actually can be sensible. But what I'm really interested in is the interpretation generated from that model. I have aging rates. Aging rates is how people move along that aging process. It's actually from the calibrated rate. It's smaller means people age slower. For the younger population cohort, that's really interesting. And also I have a pattern to interpret the aging effect, aging-related mortality rates. I use this function. So it all makes sense. And also this model allows us to analyze the dynamic population structure at each age, how their physiological age change. Okay, it can all be calculated. I don't have time to go through details. I'm going to skip it. So the important element is we define explicitly an aging rate. I use in the states to represent physiological age, and I use a stochastic process to capture the random nature of individual aging differently, and I am able to embed it in a larger mortality model. So what's new after almost 13 years of that research is we have an enhanced aging model. I redefine the physiological age. Enhanced in the way I'm using now a Box-Cox transformation for aging-related mortality rates. And it's a very compact and flexible model. And I will show how I redefine the physiological age index. So for this form, graphically, you can see in that three parameter H1, HMS, I'm able to have patterns. It has been all increasing, but in that concave way, convex way, and it can have different curvature. And also, I relate these results into a result I calibrate in that model for younger cohorts. The mortality rates decreased at a younger physiological age, but there is a crossover. We just postpone the disease to later age, but disease that causes death will come sooner or later. So that's what we observe. This crossover can be very easily captured by the newer version of the model, so we can have very good replication of that. So now I really want to focus just in the aging part, aging-related model. So I don't have the observation on that. I use a very special resident lifetime data from Channing House, and they live in the same community with same medical care, and they enter with a healthy situation. They are all female. So in my best control, I consider a small group of homogeneous individuals. I consider the only difference is their aging process. I try to control other elements not in a way as much as possible. So this is the survival rate, and this is the calibrated model. You can see it fits really well. What I mean, and I have that physiological age, it's the in that Markov process. This is the process, and I define a physiological age by making a linear transformation. So for someone 100, I can also have 100 years of physiological age, and each individual is different at the same chronological age. So I'm able to provide a distribution. They move forward because they get older, but they don't move in the same linear way. That's why I have a distribution moving forward. So you can see at age 60, the physiological age distribution is like this, and when it's moved forward, it's actually spread out. That's, I think, consistent with what I think it should be, right? Because you start homogeneous, but you get more heterogeneous. So this is very interesting, and I also have a simulated study from the Brass model. Okay, I have 1 minute. It doesn't matter. I can have more examples in a different other real life situation or simulated situation. I can do very well. Use my model, and it's calibrated to different situations. And if you are interested, you can look at the paper. So I will jump to the summary. So really, we provide a modeling approach that describes the deteriorating feature of accompanying the aging process. Okay? But aging process is explicit. It should be considered differently from aging effect. And I have a very compact and flexible model. The parameters can be calibrated to the aging-related mortality rates. And the model can be, I have all the studies to enhance the statistical aspect. So we have MLE estimations. Our parameters are interpretable. So I try to summarize the results in this 2007 paper and in the latest paper. I also have a separate paper using observations other than mortality rates, other aging effects. So it all can incorporate in this model, okay, to come up with an aging process. We don't explicitly observe, but from this model, we can summarize some idea about how underlying aging model is progressing. So I also want to mention, I start my research interest in mortality risk from reading this journal is from 1998. And I also see some Gottman sitting here. I'm very pleased I'm honored to tell you your paper, searching for a law for cause and effect, is really something inspired me to not do just statistical model, Likert model, all those other models, because it's only looking at the data without understanding on what's going on, what's really driven the mortality change. So your paper is the inspiring one. For me, I want to acknowledge your work, and that was 20 years ago. So I just made this modification because I noticed you are here. I thank you very much for your attention to my presentation.
Okay, thank you very much. So, Leonid Gavrilov will take the floor for the discussion. He is an expert in biodemographic studies of human aging, mortality, and longevity. He has over 25 years of professional experience in biodemographic studies, and he has published more than 80 scientific papers on related topics in collaboration with Dr. Natalia Gavrilova. Their book, The Biology of Lifespan, a Quantitative Approach, which you may all know, is cited as recommended reference by the Encyclopedia Britannica. He's a principal investigator of several award-winning research projects funded by the SOA, the NIA, the European Union, and the U.S. Civilian Research and Development Foundation. He's an editorial board member of various scientific journals, peer-reviewed journals, experimental gerontology, rejuvenation research, and advances in aging research. He's currently working at the Academic Research Centers, known as NORC, at the University of Chicago. He's a fellow of the Gerontological Society of America. Please, Leonid.
Hello. So I will try to be short to allow some time for questions and discussion. We have two very interesting papers and very stimulating for discussion. The first paper, what caught my attention is that lifespan is so unpredictable. So you make a lot of investment in good mathematics, try very hard, and in the end you come to the result you can say nothing for the future of human lifespan. So everything can happen. And my thought was, how can you improve the situation? How you can add some sense to make more accurate in your predictions? And in this direction, there are several ideas how you can improve the situation. One is to take into account that rates of mortality change, of course, they should depend on age. And in the model that was presented in the first paper, the first coefficient K1 is a function of time, but it is not a function of age. So maybe it might be good to add age consideration, because we do all know that trajectories of mortality are different for different age groups. And one of the examples is that if you analyze data for United States, here is the time from 1940 for 2020, and here are the death rates in log scale for different age groups. You can see that there is a decline of mortality in all age group except centenarians. So for centenarians, for 80 years, there is no significant improvement in declining in mortality. And of course, this can make profound effect on forecast for the future. So simple extrapolations or assumptions that time changes are the same for all age groups are not applicable, at least to age group 100 years. And the evolution of mortality in the United States comes from the initial trajectory, which has some mortality deceleration, to almost perfect Gompertz plot. So the log of mortality rate as a function of age in the age interval 80 years, 90 years, 100 goes according to the Gompertz line. So I think that we need to consider to revise, to make kind of revolution in human mortality database and to replace Canista model with Gompertz model, because we know that on more recent, more accurate data, you do not see mortality deceleration, you have wonderful Gompertz curve. So that should be taken into account, and that may have profound implications for measurement of life expectancy at old ages and forecasting the old ages. And we call this phenomenon Gompertzialization of the trajectory of mortality. So when you analyze data more recent, they more look like the Gompertz curve when the logarithm of mortality rate increases exponentially with age. Linearly for log, but exponentially for the function. Okay. The second suggestion how you can probably improve forecasts for the future is to take into account that the model may be additive and may be multiplicative per components. And it is important to understand that for all the historical periods, there were completely different rules of the game, because people are greedy. They believe that they will collect more and more data for old age intervals. They have better predictions. But the problem is that for old data, you have different dynamics of mortality. And here is the historical example that illustrates this idea. So here's age, here's death rates at group age 40, and there was decline in mortality historical from beginning of our century until 1970s. But if you analyze these mortality trajectories by the Gompertz-Makeham equation, you will find that the decline in total mortality was mostly due to Makeham parameter, which in 1950s became close to zero. And the Gompertz part at age 40 was surprisingly stable in history. So the evolution of mortality was due to Makeham parameter, and then when it became close to zero, there was a period of stagnation in 1970s historically. Now we have, and the same, you can analyze this data more accurately without assumption of the Gompertz-Makeham formula. You can simply make factor analysis, and one factor is have loadings to young adult age, it's analog of Makeham-like parameter, and another is factor loadings for old ages, it is like Gompertz-like parameter, and you can see that that initially historical decline was in mortality was due to decline in Makeham-like parameter, and then it became flat. And now what you have evolution in decrease in death rates due to parameter that is related to old ages. So it's completely two different things. And if you wish to improve your forecast, just forget about the old story, just to erase it. Or if you wish to analyze all the data, then please take into account that there were completely different models. That today you can apply multiplicative model like it was in this paper. But if you analyze all data, you need to consider additive models when the causes of death are added up. There is not multiplication, but additive model. Okay, then I will move to the second very interesting paper discussing mathematical models. And here is this model. And what is interesting here is the assumption is made that the rate of transition is exactly the same. So when you deteriorate, all steps of destruction are the same. And this is an assumption. It is interesting to try to test it on whether this assumption could be tested against real data and what other theoretical basis for these assumptions could be. This is not the only way to think, because there is an alternative assumption that we deteriorate in accelerated way. There is an avalanche. For example, when you have cancer cells and you transmit to next situation when you have one more cancer cells, this transition the rate of transition is proportional to the number of cells you already have. Or if you have some number of functional cells that die out, the functional load to remaining cells increases. And the loss of the functional cells accelerates for this reason, because they have more functional load. So there are biological and medical reasons to believe that this is not uniform process. This is accelerated avalanche-like process. And in this case, the model becomes a little bit different. You have these steps of destruction with accelerated rate of destruction. And then the more damage you have, the higher are the death rates. And this model produced Gompertzian formula, traditional, so it's exponential function. And it was considered 20 years ago in 1991 in our book, The Biology of Lifespan. Okay. Good. Thank you. Okay. So next thought, just for discussion. So it's a very interesting paper, but we need some topic for discussion. In the paper, the number of stages for organism destruction phases was estimated something between 100 and 250. And it is also a very interesting question how it relates to biomedical information. What is the evidence that you have this number of stages of destruction? Because one idea is that probably this approach is too granular. We need to have more fine consideration, because we are multicellular organisms. And what counts is the number of cells, the number of functional cells you have. And because we are so large animals, we have thousands of these cells. So the number of stages should be much higher than hundreds. It should be thousands, if you think in terms of number of cells. Or maybe somebody in the audience can have some ideas that should be less number of stages, but then it should be some biomedical justification why there is only hundreds of phases. So what's the justification for this, biomedical justification? And there is nothing bad if you have enormous number of transitional states, because mathematically situation becomes even easier, because you can get solutions in closed form if you have infinite number of stages, like it was in avalanche models. So there is nothing scary to have many stages, but in this case you have good biological justification that you have a huge number of cells and you progress with age, either losing functional cells or getting senescent cells, getting cancer cells. So that's the mechanism of coming from one stage from another. And then I would like to say that these are both very nice papers, and both papers have great potential for further developments, because I have just emphasized what are the interesting things in this study to discuss. Thank you.
Nothing. Okay, go on, please. Yes, go. Yes.
Okay. So thank you for your question. That gave me an opportunity to actually point out to two more detailed features of this model. So if you allow me, I will go back to my slides. Yeah, so the main reason, like you have two very good questions, but I don't have time to discuss the details of this model. So one question is about the assumption of that lambda. And so in our model, we assume it's constant. And actually, this is not an assumption about observed aging rate is a constant. I have to go to much more detail to discuss this model to make sense of what this parameter mean. But I can give you a rough idea. I have this process. This process is not something we can observe, like where we are at the current moment. Is a model to capture the progressive feature. So the assumption of constant lambda actually means, because we have two directions, one is aging process, another is aging effect, we have to fix one element to talk about another element. If we allow two elements to change, to interact, we are in that uncertainty principle zone. Because you talk about two things interact with each other, it's uncertain if you don't fix one element. So in order to fix one element, we are partition the whole process in this way so that aging rate is a constant, so that we can talk more accurately about the aging effect. Okay? So that is not an assumption about actual aging rate for any specific aging variable. It is a model setting so that we can fix some feature about aging, and then we can talk about aging effect more accurately. So that's to respond to your first question. That is indeed a very critical question, and we answer in detail in this paper and in future papers. Okay, so another response to the question is the number of days. The number of days is another critical element. It's actually, the short story is like Carl Baden. He takes his photos every day. Another approach is he can take his photos every month or every year, right? So numbers in this process is really, that's whatever we need to be able to measure more meaningful. So it's again related with what kind of aging effect you want to talk about. So that is another thing. It's not an assumption, it's more a model setting so that this model can be more useful or meaningful for a specific aging effect. So when we talk about mortality rates, because it's mostly annual rates, but if we talk about something that you can measure more constantly, the M should be adaptive accordingly. So these two features, I definitely need another 20 minutes or 30 minutes to go through details. But they are very good, important questions so that for me, through the understanding of the model. Thank you very much for your question.
I think we will open to the audience. If any of you have a question for one of the two presenters or reacting on our discussant, I would say, but Sam is already at the mic. Please come up to the mic because we are recorded.
Sam Gutterman, question for Mr. Schupp on it seemed like a really good paper. The question of trends. In particular, you mentioned U.S. male trends. The most recent decade has shown a couple of potential significant trend changes. One, 2011, approximately to 2017, where there's been a slowdown due to deaths of despair in cardiovascular diseases. In the most recent 5 or 6 quarters, a change, again, a significant improvement. But obviously, there's only a year or so experience. How do you and this is probably trends that are shared by over different countries. How does your approach address or try to identify these changes in relatively short period trends?
Well, thank you. Can you hear me? Yeah. Well, thank you for your question. The problem with the calibration with respect to the latest observation, you simply don't know whether there is a trend change or not, or it's only random fluctuation. You only know it when you observe 4, 5, 6 years on that trend. And therefore, we think the uncertainty in the starting values is in some cases very large. Also in the U.S., I showed that figure for Kappa 1 where we have several trends in it, and some realizations of these trends had trend changes in the latest years, and some other realizations simply hadn't. So I think the uncertainty is very large, but you can't say it for sure.
Other comments? Questions? Jean-Marc?
Jean-Marc Fix, it's really a comment for both. So I think it's very important, and it answers a little bit or addresses a little bit Sam's issue, the difference between a statistical model that works well and trying to find an underlying mechanism for why the model makes sense. There are many models that can make sense, and most of them don't approach reality. So from that perspective, those models are interesting in highlighting potential value for trying to explain that. But I think is a danger, and that's why we have those big uncertainties on interpretation of the edges of the model for the model of trends, whether this is a new trend or not, and then projecting that 20 years in the future, you could have huge errors that are, from a practical perspective, unusable. So that's just my comment.
Maybe one comment from my side on that uncertainty. I agree that it appears to be quite large, but you have to consider we looked at forecasts 50 years into the future. And when we analyze the recent evolution of that trend, either it is totally flat or it's even steep, then when you consider the values in 50 years into the future, the uncertainty is quite huge when you extrapolate this trend. So somehow one message of our work is that the uncertainty when you look at long-term forecasts is simply very huge, and you should consider that.
Hi, I'm Steve Goss from U.S. Social Security. Just sort of following up on Sam's point. When you see a change in the statistics and the data that are coming forth, when do you believe, when do you think that this is like change in trend? And by way, change of trend, of course, as you've all pointed out, can be change of trend for a little while, or it can be a real seminal change in trend going on for a very long period of time. And of course, we never know. But what I would suggest is the one thing that we have always done at Social Security, and I presume everybody else is, when you see a change in the data, the very first question is, what's underlying this change in the data? More than once in a while, we find that there is something that has changed in the way the data is collected, or some problem with the data. Occasionally that happens. or there could be some more underlying, really fundamental changes that will be long-lasting and persistent. And those are really the questions that are very fundamental. I just point out to you, I assume everybody's very well aware of the work that was done by David Blake and others about phantoms never die, where it was observed in the UK. I don't know if Adrian Gallup was here, but it was observed in the UK that there was this big shift by one cohort. And it turned out later on when they looked at it more carefully, well, there were some issues with the data that it made it look like that one cohort was dramatically shifted from the prior. So really the very first and foremost when we see a change in data, especially over a very short period of time, is what caused that, what's the bottom line for it, and therefore is it something we should just ignore because it's an aberration, or is it something really fundamental that we really believe is going to persist for a long time?
Can I respond to those two comments? Although it's not my presentation here, but I also do research on that regard. I have a further comments to add to this discussion, because I actually, two further comments. One comment is this kind of model, I did it before. I didn't present here. I think it's still useful, but useful in what sense? I wouldn't use it for prediction per se, because it can be so wrong. But how I would use this model for? It's used to measure the uncertainty in the future. So I think that is how I would use this model. I wouldn't use the scenario of this model generated us to say this is very likely, But the uncertainty measured maybe, help us to understand the future mortality uncertainty. So that would be how I use this model. So that's one comment. Another comment maybe. I hope you don't feel it's negative feedback, but I think it's very dangerous to use those complicated model for forecast, even for uncertainty measurement, because the first step is to decompose the real data into K1, K2. And you already distorted the data into this variable. What if the future trend cannot be properly modeled by this model? So it's already biased somehow a perspective using this model, because you really have to have the belief in the past interpreted by this model can be followed in the future. And all the trend changes are based on K1, K2, I found it's very dangerous to use forecast based on the analysis of this. So that's my two comments to add to this kind of question. So that's why I focus more, relate back to my research. I would like to focus more on understanding what's driven mortality change. So the model I provided is more to provide a quantitative method. We can summarize the aging effect in the past. But it's not for forecasting purpose. It's more, I think we need to understand more to do prediction. I just feel so scary on so many complicated model making a lot of statements and cannot be related with actual evidence. I'm not talking about your work. I feel sorry if it sounds negative, but it's from my personal research experience.
Yeah, thank you for the comment. I think when you look at forecasts 50 years into the future, there might be some paths in a simulation approach. It's random simulation, so there are always some paths, or can be some paths which are not very meaningful. For instance, when the kappa 2 parameter in a CBD model gets negative, then you have decreasing mortality curve. So you always have to carefully monitor the scenarios you generate. But that's, to my opinion, not only a thing with our trend model, but with every simulation you make.
If there is one small comment, short question, otherwise we will close the session. Thank you very much to all three of you, and bon appétit.